Welcome to the last video on Chapter 4, and indeed the last video on the AS FM1 course. Here we're going to be looking at successive direct impacts, so there's nothing new to learn. It's just more the exam style questions where we have a number of impacts in a given question. So we'll get started straight away with example number 11. We have three spheres A, B and C of masses m, 2m and 3m. And they're moving along the same straight line on a horizontal plane with A following B and B which is following C as we have in our diagram. Initially the speeds of A, B and C are 7, 3 and 1 meters per second. A collides with sphere B and then sphere B collides with sphere C. We're told that the coefficient of restitution between A and B is 1/2 and the coefficient of restitution between B and C is 1/4. So our same before and after diagram here. Part A asks us to find the velocities of the three spheres after the second collision. So we start by concentrating on the first collision between A and B. So if I put velocity of A and the velocity of B as our unknowns, we now need to find out, as we were in the previous exercises, two unknowns. We need two equations. One comes from the conservation of momentum and the other comes from the coefficient of restitution. So the conservation of momentum tells us that we have 7m plus 6m, 3 lots of 2m, that's the total momentum before the collision, equals the momentum after. So mva plus 2mvb. Again, we can divide the equation by m, and that leaves us with 13 equals VA plus 2VB. We're also told the coefficient of restitution between A and B is 1/2. So 1/2 is the speed of separation, which will be VB minus VA over the speed of approach, and the difference between the speeds there will be 4. So therefore we have 2 equals VB minus VA. So VA is going to equal 3 meters per second and VB is going to equal 5 meters per second. Now we can put our second collision in place. So B is going to continue on. So our initial speed before the collision with C is going to be 5, and we need to find out the velocities afterwards. So again, we can have VB2 for example and VC, just to show that will be different from the first. So our second collision, same as before, the coefficient of the conservation of momentum is going to be 10m plus 3m equals 2m VB2 plus 3m VC. So again, if we divide by m, that leaves us with 13 equals 2 VB2 plus 3 VC. And if we look at our coefficient of restitution, we have 1/4 this time is the coefficient of restitution between particles B and C. So 1/4 is going to equal VC minus VB2 divided by 4. So therefore 1 is going to equal VC minus VB. And that tells us that the velocity of C is going to equal 3 meters per second. And the velocity of B this time will be 2 meters per second. So therefore we can now answer our question. So the velocity of A after both collisions, that's still travelling with a speed of 3 meters per second. The velocity of B is now going to be travelling with a speed of 2 meters per second, and the velocity of C is going to be 3 meters per second. And the final question asks whether there will be a further collision between A and B. Well, the velocity of A, as you can see there, is greater than the velocity of B. Therefore, a further collision will take place. Okay, moving on to example 12, we have a little bit more algebra here. Otherwise, it's the same sort of question. So in example 12, we start with particles of mass 3m and m. and we have speeds of u and 2u in the opposite direction. That's particle p and particle q. And we're told that after the collision, the velocities of p and q are v and w respectively, given in the direction of motion of p before the collision. So, same two questions again. We have the coefficient of restitution is actually e, and we're asked to find v and w in terms of u and e. So it's the same two equations. Conservation of momentum, first of all. Because we've got things in different directions, it's worth reminding ourselves which direction we're taking is positive. So we have 3mu minus 2mu, which is our momentum before the collision, is going to equal 3mv plus mw. Again, we can divide by m, leaving us with 1 equaling 3v plus w. Our coefficient of restitution, we have E is given as E, so our speed of separation is w minus v divided by the speed of approach, which is 3u. So we have 3eu equals w minus v. To rearrange these, no matter which way around we do it, we need to find both v and w. So if we set w here to equal 3eu plus v and substitute that to replace w in our first equation, so we have 1 equals 3v plus 3eu plus v. So therefore 1 minus 3eu is going to equal 4v. And I've just realised obviously that's always been 1u. So therefore if I take out my u, I end up with 1 minus 3e all divided by 4 equals v. And we know that w equals 3eu plus v, which is u over 4 multiplied by 1 minus 3e. So that would be 12eu over 4 plus u over 4, 1 minus 3e, which will then give us that w. So we've got 12 minus 3 eu over 4, so that will be u over 4, 1 plus 9e. So we have our velocities of v and w after the collision in terms of u and e. Now part B goes that, or suggests that if the direction of motion of p is changed, so if the motion of p is changed, if we just go back to our original diagram, that means that v has to be less than 0. So for part B, we have v is less than 0, and v we now know is u over 4, 1 minus 3e. So we know that that must be less than 0. So since u has to be greater than 0, we can therefore say 1 minus 3e must be less than 0 to make the whole thing negative. So therefore 1 is less than 3e, so e must be greater than 1/3, which is what we were asked to show. And then finally moving on to part C, I've left our values for v and w from the first part because it says given that e equals 5/9, we then have to show that p and q collide again once q has collided with a vertical wall. So I want to start by finding the values of v and w given that e equals 5/9. So v is going to equal u over 4, 1 minus 3 lots of 5/9, which is going to be, so minus 6/9 u over 4 there. So therefore v is going to equal minus u over 6, and then w is going to equal u over 4, 1 plus 9 lots of 5/9. So therefore that's going to equal 6u over 4, which is 3u over 2. So now we have those values, we can look at what's happening to q. So q is going into the collision with the vertical wall with a speed of 3u over 2, and it rebounds, if we just call that the velocity of q, and we're told that e is that value there. So if we now just move these up slightly. So the coefficient of restitution with our collision here, we're going to have that E dash is going to equal the speed of rebound divided by the speed of approach. So therefore VQ is going to equal E dash 3U over 2. Now, it asks us to show or find the inequality, the values for the E dash, so that there is a further collision. Now, this was obviously travelling, if we look at perhaps just the particles now after the collision with the wall, we have particle P is travelling with a speed of U over 6, and obviously we have our equation here, or sorry, our variable, our unknown I should say, of 3U E dash over 2. So for there to be a further collision between P and Q, we know that 3U E dash over 2 must be greater than U over 6. We can divide by U, giving us that E dash must be greater than 2 over 18. Therefore, it must be greater than 1/9. And again, just to clarify, we should really say that our values for E dash could be anywhere between 1/9 and 1. As we should have really said in part B, if I just bring that down again, in part B we shouldn't really have left it as E is greater than a third. It should really be 3 is third rather is less than E, which is less than or equal to 1. As we know, our value for E varies between 0 and 1.